Hello everyone. If you're watching this right after taking the SMO Junior round 2 this morning, I hope it went well for you. Now the SMO round 2, as we mentioned in the earlier video, is always difficult, right? So regardless of how your friend did, regardless of how you did, please do not be too discouraged, and also take it as you've had 3 hours to look at 5 really difficult problems, and now we can look at it together and learn from some interesting ideas and possibly see where you have potentially gotten some marks and where you may have missed some marks. So let's begin immediately by looking at question 1. So our first problem is a geometry question, and usually geometry questions are, well, I wouldn't say easy, but geometry questions for the junior round 1 tend to only require a few simple ideas. Similar triangles, Pythagoras theorem, area, and maybe a little bit of just angle chasing to tie it all up. So we don't expect things to be too bad. Let's try to draw a diagram first. So I've got a quadrilateral ABCD. Diagonals intersect at O. And then M and N are points on the segments OA and OD respectively. So M is somewhere here. Suppose that MN is parallel to AD and NC is parallel to... Whoops. It can't happen, can it? How do I put N such that CN is parallel to AB? Okay, so I realized that maybe I should just redraw this entire diagram again in a different way. Now this will happen, right? When you are given a question without a diagram, the first time you do it, it may not quite look as correct as you hope. So let's try again. This may look very familiar. Like, didn't I just draw that? I think I learned my lesson. Right, so I would like to put N such that NC is parallel to AB. So I've actually done the same kind of a drawing, but labeled it differently so that at least that's okay. CN is parallel to AB. Whoops, and of course I realized that I should put my A and B the other way around. That's the correct order. So MN is parallel to AD, M is on OA. So this is my diagram. I've got a pair of parallel lines here, and I've got a pair of parallel lines here. The question asks me to show that angle ABM is equal to angle NCD. So BM I shall draw in. Angle C is, well, already there. So I would like to show that these two angles are actually the same. Now let's just remember that we don't know it yet. That's what we would like. Now usually when you're solving a question, you solve it backwards, but then you explain it forwards. So when I solve it backwards, it means that I ask myself the question, why should that be true? You see that AB and CN are parallel lines, which you can describe as they are facing in the same direction. So in order that the angles marked in yellow are the same, it means that CD and BM should also be parallel. How do I show that? Now, in order to show that CD and BM are parallel, if you just tried doing a little bit of angle chasing using the two pairs of parallel lines, you realize that we don't quite get that because the only reasonable things we could try would, let's say, be looking at alternate angles, like hopefully these two are equal, but it is not that easy to actually show that. So let's put that aside first, and instead ask ourselves, how else could I show that they're parallel? Now, to show that they're parallel could also be via similar triangles. And the similar triangles, so I'm going backwards. It could be triangles from O, so OCD similar to OMB. That would be enough. Now, how do I show those are equal? Sorry, those are similar. Since there is already one pair of vertically opposite angles, if I wanted to show it, it means that by SAS, I could show something like OM over OB is equal to OC over OD. Right? That would do the trick. Now let's note down those lengths that I've just described. So we have got OM, we've got OB, OC, and OD. Now, what we may realize is that these lengths all seem related to the parallel lines that we know are there, right? The MN being parallel to AD, there's OM and OD. CN parallel to BA, there is OB and OC. So these are quite good sounding. So I should now go forwards and look at my similar triangles involving those lengths. Alright. In my lessons, I often talk about hourglass patterns and pyramid patterns. So there is this hourglass pattern here. That first pair of similar triangles would relate to OB and OC. So OCN is similar to OAB, means that OC over ON would be equal to OA over OB. Right? And I'll just circle the two things that we like, OC and OB. The other pattern is our pyramid pattern, and the pyramid pattern would be on this side, which would tell me that ONM is similar to ODA. So if those are similar, then again I want to make sure I involve OD and OM. So ON over OD equals to OM over OA. And so again, circle, these are the ones that I care about. But hang on a moment. These two are the same, ON, OA, ON, and OA. Which means that if I were to cross multiply, OB times OC is equal to OA times ON, and OA times ON is equal to OD times OM. So that will relate my four lengths together, and these collectively would give you that. OM over OB is equal to OC over OD, and then since we're working backwards, we can complete our proof this way. Now, of course, when you actually write it, it means that you start in the direction I've shown. You will begin by mentioning this triangle and then this triangle, and then after that you will get the equation, come back here, and then after that say that the lines are parallel. And finally, of course, we have to just say a quick word as to why that would guarantee the two angles are equal. So why would the parallel line there guarantee it? Now you have more than enough reason to angle chase. So I would then just say that angle ABM is equal to OBA minus OBM. The OBA is going to be ONC from the blue parallel lines, and OBM is going to be ODC from the new red parallel lines that we have just discovered. And ONC minus ODC is indeed equal to NCD. So that's our first question. I would say this is a fairly normal geometry question for the second round of the SMO Junior. Next up is question 2. What's the maximum number of integers that can be chosen from 1 to 99 so that the chosen integers can be arranged in a circle with the property that the product of every pair of neighboring integers is a 3-digit integer? My starting intuition would be that 3-digit integers are kind of like in between, right? Because you know that the maximum versus the minimum, the small ones will look like, let's say 1 times 2 is 2, right? So you have got very small products. 2 times 5 is 10. 3 times 12 is 36. So you've got some very small products which are too small. And then your maximum would be, well, 98 times 99. This is 9702, basically quite close to 10,000 and very far away from being a 3-digit number. So 3 digits are in between. And 3 digits are in between, meaning that you would fail if you end up with small times small. And you would also fail if you end up with a big and big next to each other, because 2 big numbers are going to give you quite easily more than 1,000. And 2 small numbers are going to quite easily give you less than 100. Now, I want to be a bit more precise in what do I mean by small or big, right? Is 10 big? Is 20 big? Is 50 big? Is 8 small? Is 18 small? So we need to ask ourselves what exactly is considered small and what exactly is considered big. Now, before we do that, we realize that I can't actually use 1 to do anything, because 1 times anything is going to be just that number, which cannot be 3 digits. So 1 is actually useless. From the other numbers 2 to 99, what I could do is something like this. I ask myself, what would be the limit whereupon big times big will exceed 1,000? Do a bit of calculation. 30 times 31 is 930, is our starting point. 31 times 32 just fits in, and 32 times 33 exceeds it by quite a bit. So which means that once you go past 32, I can call that big, because 32 times 33, and therefore anything that is more than 32 times another number that is at least 32 is going to exceed my limit. So I'm going to call it big numbers are just everything from 32 to 99, and I'm going to call small numbers everything from 2 to 31. I don't want to include 1 because, as we said, that's completely useless, so I don't want to accidentally put it in. Now, basically what we need to do is to do a little bit of social distancing. These guys need to be socially distanced. They cannot be next to each other, and so our small numbers are going to be kind of like buffers. You can call them masks if you like the COVID theme. So they are like buffers in between, which means that if you want to put in a lot of numbers, you would go big, small, big, small, big, small, big, small, and you will run out of small numbers first before your big numbers. I've only got 30 small numbers. So my current idea is that I'm going to go big, small, big, small, big, small, and just loop around and use 30 of each. Now I hope that if I do big times small, it will just fit into the correct range. And then I've never got small times small or big times big. So this seems good so far. There is, however, one small problem if we try to do this, which is that the big numbers, of course, you can't combine them, but some small numbers also cannot be combined with big numbers. And the biggest culprit is, well, the biggest small number. This guy is a medium number, because you realize that 31 times 32 is okay, But 31 times 33 would already be too big. That is not okay. So I can't actually do this. This fails because 31 can only be next to the one big number, which is 32. Right, so you can only touch 32. It's supposed to be touching something on the left and right. Remember, this is a circle, not just a long line. And so therefore, it can't be 30 big, 30 small. And so maybe the 31 needs to touch something else, right? 31 has to also touch a big and a small number. So the next thing is I try 59 numbers. So 29 big and 30 small. I don't mind 31 being one of my small numbers still. It's just that it needs to be on one side next to another small number. Now, what are these 59 numbers? Well, the big numbers, I think the easiest way would be to just pick them in order from 2 to 30. Sorry, 2 to 60. Right? So that the numbers are in consecutive order. And then we kind of just reason things out, which is that we have already said 31 can only touch 32. And so I can say that my arrangement would have 31 touch 32 and 31 touch a small number. So I'll start by putting something like 31 next to 32, and then I will go downwards because something like 30 can only be next to 32 and 33, so 30 has to be there. And then I continue again. So we go 2 and 59, and then wait, what's the last number? The last number, so I go 31, 32, 30, 33, 29, 34. So each pair is adding up to 63 each time. And so actually it should be 3, 60, and then a spare number of 2 because I've got one more small number. Now this looks good because all of these things that add up to 63 are getting further apart, which means that from this very barely fitting in 992, I am going to get more and more space. So if we look at this and think about it, it's quite easy to resolve the only one problem, which is 31 times 2. 31 times 2 is too small. But I can just borrow some other small number and put it here because, well, 3 times 31 is still too small. So I shall grab the 4 and just swap places with 2. This is fine already. So you see, we're quite happy with this because now each of these pairings, I can just explain that most of these pairings add up to 62 or 63. Sum to 62 means that you are ranging from 2 times 60 to 30 times 32, which are all okay. And those that you add up to 63, likewise, would just be from 2 times 61 to 31 times 32 are okay. Meaning that as long as I did this throughout, all of them will fall within the 3-digit range. Which means that my answer is indeed all these 59 numbers can be put in, and we have already explained why 60 or more cannot work. Now, at this juncture, you may be asking, wait, we can't write our solution like this, right? And of course, that would be true. After you have done all this work, you would then proceed to try to write it a bit more neatly and organize your solution in a more systematic manner. But the main challenge in round 2 is first to solve the question. Expressing yourself is a separate matter, but expressing yourself is not as difficult as first figuring out what to do. At the same time, I've also attached a copy of written solutions in the description below, so you can take a look at the description and also see how the solutions could be formally written in a contest environment. Now, let's get to question 3. Now, I'm pretty excited about this one because this question was actually proposed by me. Now, as evidence of this, let me just show you a sneak peek. This is actually from my proposals for this year's SMO. So I proposed a number of questions, and this is the one that I have proposed, which was selected to be used in the SMO Junior. Now, when we submit a proposal, we usually will include a solution, and so I'm going to explain it. You may also see that there are actually, in this document, 10 pages. There were also other questions which I proposed, and just for the time being, I shall not review any of them in case something gets used for the SMO Open. Now, let's get back to actually solving this question. So, being the person who proposed the question means that I did not know in advance that the question would be selected. I do not know which questions would be. But at the same time, if you were to look at this here, maybe you have some sense of where the question comes from already. Right? The question was actually just inspired by thinking about sliding blocks around in some of those sliding puzzles. You know, there are those sliding puzzles with 4 pieces, 3 pieces, and you're trying to shift a piece out, or you're trying to arrange them in a particular order. So I was thinking about, can you go on for a very long time? And the answer would certainly be, it is possible that you just go round and round and round and round and round. So what happens now if I insist that you cannot repeat? And that's where this question came from. So you're supposed to just keep on moving dominoes. And the question is, do I have the chance to move all the dominoes or only a few dominoes? So in this example, it means that you move D over, this becomes the gap, and then you move A over, and this becomes the gap. We can think about how we can actually do this a little bit more optimally, perhaps. Now, 3 by 3 is a bit too small to see anything, so maybe you try a 5 by 5. Now, what I'm thinking about is, where should I put the dominoes so that I can slide many of them? Now, it means that anytime, the moment there is a gap, you want another domino to be able to fill that gap as quickly as possible. Right? So for instance, if let's say this is my gap, then I want to put a domino here. And when I slide it over, this is the new gap. And I want to have a new domino ready to fill this gap. So I say that perhaps I could put a domino here. And then when you shift that over, this will become the gap. And so on. So you can see the reasoning is going to look like this. That possibly I could do something like this. And down here, maybe I would have to move into the center. And then, actually, that's it, isn't it? So, you can't actually do better than this for the strategy that I just described, because at this point, you can't put in a domino that is ready to slide into that position. So this would mean that we have moved 1, 2, 3, 4, 5, 6, 7, 8 dominoes. Notice where I've shaded all the gaps. This should be interesting because we realize that when you have a gap and then a domino moves in, the new gap will always be exactly 2 squares away. It is forced to be 2 squares away. So that means that if I started off in one of these gaps, it can't be helped that you will never be able to, let's say, have the gap show up down here. It will not happen. So in fact, these 9 gaps is the best that I could do. And you also realize that the gap cannot be reused. And what do I mean by that? Now, they can't be reused in the sense that if there's a gap and then you use it, it means that a domino is now occupying that. Now, the domino has moved in, so it can't move out. So if it can't move out, that gap is just going to be there. You can't use it again. So the implication is that if the gap can't be used again, then in this case, I just need to decide where do I start from. And if you had, let's say, started from here, then the only places you could go by moving 2 steps at a time will be something like this. That's not better. So to describe this, basically what we can do is to just number the squares. Let's say 0 to 4 in our small grid, and then just say that there are just 4 types: odd, 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 even, odd, and even, even. And you can only shift within your own group. So the odd, odd here would be the worst because there's only 4. The odd, even, odd will both have 6, and the even has 9. So that's nice. And the same strategy works for the 2023 by 2023 grid. If I want to label it like this, 0 to 2022 on both sides, that means that your even, there would be 1012 even numbers and 1011 odd numbers. So you get 1012 squared of the even. And for your odd even or even odd, you only get 1011 times 1012, which is inferior. And for the odd odd, you just get 1011 squared. This is most of the solution. So you must mention that this is the highest. You mentioned that gaps cannot be reused. Otherwise, why can't I just use that gap over and over again and then just keep moving dominoes around? But the last thing is that you need to say how this will work. And you've seen this spiral pattern here. That's one way you can make it happen. Another way you can make it happen would just be using a snake pattern. So this would be of size 2023, means that you've got 1011 dominoes and a blank. This would use up all of these in the first column. And then our next concern is getting everything in the third column. So we just repeat the process by going down this way. And then just have essentially a giant snake. Now, obviously, if you have this giant snake, it's going to be using every of these gaps. And so we are fine. It is going to still cover all this 1012 squared we mentioned. So it can be used using this snake pattern. And the number of moves, therefore, because you started off with one gap already, is 1012 squared minus 1, just like the 3 squared minus 1 just now. Now, many of these questions, including this one, which I proposed, were with just an idea of a question and no idea of an answer. Thought about it, spent a moment wondering why can't I seem to do better, and then found an explanation, and then that became the question. So I would encourage you, try setting questions on your own. Try thinking about things, especially if let's say you're trying to improve your algebra, just try manipulating algebraic expressions. If you're trying to improve your geometry, try drawing random stuff and see what you find. You'll be surprised at the number of interesting ideas you can come up with. And as you get better at setting these questions, you certainly get better at solving these questions as well. Let's carry on to question 4. Question 4 is actually quite simple for a question position at number 4. I would say that it's probably one of the 2 easiest questions. Two-digit primes are written one after another in 2 different ways to form 2 4-digit numbers. For example, 11 and 13 give you 1113 and 1311. Now, if the 2 4-digit numbers formed are both divisible by the average value of P and Q, find all possible pairs PQ. This is actually a quite easy question to convert into a mathematical statement. Average value of P and Q is obviously P plus Q over 2. If they are 2-digit primes, both of them are odd, so this actually is a whole number. The question does make sense. 4-digit numbers with P and Q put next to each other would basically be the 2-digit number followed by the 2-digit number, or vice versa. The first one would be 100P plus Q, and then the other would be 100Q plus P. Rather, it's not or, it's and, because both of them are multiples of P plus Q over 2. So I'm trying to figure out what's strange about this, right? What can go wrong? And usually what you would do is to try to eliminate some variable. So P plus Q over 2 is a factor, means that I can list out some interesting multiples. Well, it means that P plus Q obviously is a multiple of P plus Q over 2. And so now if I subtract it off from both of these, 99P and 99Q would also be multiples of P plus Q over 2. Now that means that the P plus Q over 2, some parts of it could have come from the 99 and some parts of it could have come from the P or Q. But PQ are prime. Now if PQ are prime, you know that prime numbers are basically not going to help you halfway. Either it helps or it doesn't help. And p plus q over 2 is the average, which means that one of these prime numbers is just bigger, so it doesn't help. For example, if I want a multiple of 6, 7 is not going to help. Therefore, I'm just going to first put in, for convenience, that without loss of generality, p is less than q. If p is less than q, then this would mean that q is more than the average, and q is prime. And so p plus q over 2 and q must be relatively prime, because q has no factors other than 1 in itself, so the only common factor could be 1. And if it's not helping, that means that p plus q over 2 is a factor of 99, which is a number and is always our objective. We always want to get to a number. So p plus q over 2 is a factor of 99. Not many possibilities, because p plus q over 2 can't be that small, can't be that big. They are 2-digit. So it is at least going to be 12. And of course, it's going to be less than 99. And so being stuck in between, the only possibility is that it is 33. And p plus q is 66. Now, before I list out, I want to see, should I expect all of them to work, or is it only some combinations that add up to 66 that would work? But actually, if you look at 100p plus q minus p plus q, which is 99p, we're basically saying that these are going to be 99p plus 66 and 99q plus 66. And this is going to be 33. Obviously, 33 is a factor of both of these. So any such PQ work. And so we just need to do a little bit of prime listing. So start with 11 doesn't work, 1353 works. The next one that works would be 19 and 47. And the next one that works is 23 and 43. And then 29 and 37 is the last one before you just get the reverse orderings. So that's 8 pairs, but 4 or 8 depending on whether you assume that they are considered to be the same or different. And finally, we come to this question 5, which is the reason why this video is not out about 1 hour ago. This question 5 caused a big headache because I couldn't find a simple explanation, and I was pretty stubbornly trying to find a simple explanation. And then I realized that I can't find a simple explanation at all. And I can't find a simple explanation because I essentially confirmed that algebraically this is equivalent to a hard question. So if you can show that this is the same as a hard question, then the hard question has no easy solution. Then this is the same as that hard question. It has no easy solution. So you would have to bear with me for what is going to be a very premature introduction to what is called Vieta jumping. Now, as I've remarked in my solutions, Vieta jumping is a very new thing to the SMO. It was introduced long ago in the world of the IMO in 1988, but in terms of our SMO, it seemed to be off limits, and then suddenly it showed up in senior last year for the first time, and then now it has somehow found its way to junior, which is frankly quite baffling to me. But at the very least, it is possible to get an answer mark for this first. So our answer mark for this would come from just trying stuff. K equals to 1 clearly fails and 2 clearly fails. And if you try k equals to 3, you'll get something like a squared plus 4 equals to 5b squared. Obviously 1 and 1 work. Then you can continue to look at are there any other possibilities, and you will seem to fail, but there isn't a simple explanation why it fails. So the others fail for varying reasons. Now the varying reasons would include stuff like if you try mod 3, some of them will die. You try mod 4, some of them will die. And then after that, there isn't any systematic explanation though. Some of them you just do a bit of listing. And so this is very weird. Now, since all of the modular ones don't work, so my next intuition will be, let's try to do some bounding arguments though. So a squared plus 4 is equal to k squared b squared minus 4b squared. I'm thinking that potentially an issue is that we have got a lot of squares here, right? All these things, a squared, k squared, b squared, 4b squared, and 4 are all squares. But I'm thinking that maybe if I were to just look at one of these here, is it possible that you are going to have an expression which is just a bit more than a square and hasn't yet reached the next square? And so this leads me to something like saying that actually a squared is just k squared b squared minus a bit. Now I say a bit because k can be very big. So if let's say imagine k is 99, that's going to be 99 squared of b squared, and then you're just minusing off 4b squared. So that's a bit compared to if k is big. Right? And k is big is our concern, because if it's 1, 2, 3, 4, 5, I could just list out possibilities. I'm concerned about bigger ones. That's my headache. So a squared is k squared b squared minus a bit, and so we can try something like a equals to kb minus c and substitute that in. Right? So that I don't have so many squares. I want to cancel off the most messy looking one, which is k squared b squared. Now, this is just a substitution. Of course, a is going to be something less than kb. I don't know how much less, but if I put it in, and let's just cancel off the k squared b squared. I'm left with this, which if I make k the subject, k would be equal to c squared plus 4b squared over 2bc. Now we know that by MGM, actually 4b squared plus c squared would be greater than or equals to 4bc, so k would be more than 2. But 1 and 2 is not really news to me. I already knew that 1 and 2 are not going to work based on this equation, so that's not really helping that much. I do, however, have something simple to do, which is that this is a 2 here, this is even, and this is even. So clearly c is even. And I can let c equals to, let's say, 2x. Okay, and that will allow me to cancel off all the 4's. And when I cancel all the 4's, I'm going to be left with x squared, b squared, and 1 over bx. Now, this is actually quite famous. That the sum of squares plus 1 over the product, the only integer value is 3. No other integer values can be obtained. But the trouble is that even though no other integer values can be obtained, the proof of it is not actually that simple. unless you have already heard previously of Vieta jumping. So take this as just an introduction to 99.9% of you as to how this will work. So how Vieta jumping goes, as the name suggests, is to use Vieta's equations and view this as a quadratic. So I shall move this back into a quadratic again. And so I view it as x is a root of this quadratic. And if there's a root, there should be another root. Since it's a quadratic, then from Vieta's, the sum of these two would be bk, and the product of these two would be b squared plus 1. Now, the reason why we call it Vieta jumping, right, is that there's two roots here. I basically want to say that let me jump to the smaller one, and then the smaller one, and then the smaller one, and then once I shrink them all to very small, there won't be many possibilities left. But I don't want to describe that process, so I'm going to just pretend that this is the smallest one already. So I would paraphrase this to, so let this xb be the smallest pair that satisfies this equation. So of course, since I'll write it as since x is a solution to the quadratic, you will have another root, x prime, which satisfies this. This pair of things. Now, the other root here, we know nothing about it, but from the equations, I can gather a couple of things. So I should say positive integer pair, because we don't want 0. And so this other root, x prime, would look like bk minus x, which means that it is an integer. Could it be negative? Answer is no, because it is also positive over positive. Which means that my new root gives me another pair. So x prime and b also satisfy the equation here. And so it is not the smallest pair. It has to be at least as much as x. Then you'll want to see what looks weird about this. And what looks weird about this is the fact that, okay, so I can have added an assumption freely, which is that since it's x and b, I can always let my x to be larger than b. I can do that, right? I can also let x be smaller than b. Now I do this because x is bigger than b, and we call it Vieta jumping because it basically means that x prime has jumped over b. But that looks weird because now this means that x is at least b, x prime is at least x. So x prime, which is supposed to be b squared plus 1, but then x squared is going to be more than b squared and yet smaller than xx prime. So maybe I should just combine this like that. So you have a square that is at least b squared but less than b squared plus 1. The only way that this can happen is that x squared is b squared. It can't be b squared plus 1. And so x is b. Basically, this is saying, okay, wherever your solutions come from, the smallest one will have both of x and b being exactly the same. Now, if they're exactly the same, we put it back in, and it will just look like k is equal to b squared, and 1 over b squared, which is this. And obviously, the only integer value would be 3. If you're watching this after taking the SMO Junior today, please don't worry about this question in particular. It is just strangely difficult and not normal for the SMO Junior. If you're watching this in preparation for 2024, also do not worry too much about this question unless you're confident you can at least solve 4 questions in any round 2 paper. If you can solve at least 4 questions, maybe worry about this. But most of you shouldn't have to worry about this beyond the fact that sometimes a very innocent looking question can really be very difficult. So that's for all from me here. Please like the video, subscribe, and leave any comments below. Share your experience, but be nice because round 2 is always difficult. So thanks everyone, and see you again soon.